Okay, so this is the moment where Unit 2 meets Unit 3. And we're going to take on the derivatives for polar and parametric functions. Alright, so let's talk about polars. So recall that typically a polar has the form r is some function of theta, where r is the distance from the origin, and theta is how many radians we are from the initial vector at theta equals 0. Okay. So if I take dr d theta, that is what I get when I take f prime of theta. Okay, so what is this? This is the change in radius with respect to the rotational measure. So if I rotate 1 radian counterclockwise, what is changing as far as the radius going in and out from the origin, right? So if I have like r of theta is, let's say, theta minus sine theta inverse, or to the -1, right? Then r prime of theta, let's say that's going to give me that -1 times theta minus sine theta, now to the -2, times the derivative of the inside, which is 1 minus cosine theta. Okay, so let's say I'm now at straight up and down. So theta is going to be pi over 2. So if I'm at theta equals pi over 2, right, then r prime of pi over 2 is going to be negative pi over 2 minus sine of pi over 2 to the -2 times 1 minus cosine of pi over 2. Little simplifying here, this gives me negative pi over 2 minus, well, that's 1. Right, and this is 1 minus 0. Okay. So that just goes away because that's just multiplying by 1. So let's see, this is -1 over, let's see, pi over 2 minus 1. So let's see. So that's going to be -1 pi minus 2 over 2 squared, right? So this is going to give me like -4 over pi minus 2 squared. All right, so that's about as good as we're going to do, but this gives me a sense at which how fast we are or are not rotating. Little quick work with a calculator gives me that that's approximately -3.069, which means that at that moment at pi over 2, so like up at the top when we're pointing upward, every time that we go 1 degree or 1 radian in a counterclockwise direction, the radius is getting smaller. So what this means is at that point, if you like envision this as a particle kind of going around the origin, it's actually getting closer to the origin at that time. So this is what this idea of dr d theta actually means. It's like, how is the distance from the origin changing with respect to the current rotation? So let's take a look at this from a different perspective. It is possible for us to see this as in terms of dy dx, and this takes a little bit of working here. So this is actually the slope of the tangent line to the curve rather than the change of rate going inwards. So we're going to actually go from r's and thetas back to dy dx. So let's use this example. Let's say that r of theta is 1 plus sine theta. Okay, so we want to know what dy dx is when theta is pi over 3. Okay, so recall x is r cosine theta. Y can be parameterized as r sine theta, right? So if we have this, right, then x should be 1 plus sine theta times cosine theta, right? If I have that, which means that dx d theta, dx d theta should be then, let's see, first times the derivative of the second plus second times the derivative of the first, which is just cosine theta. Okay, so if I do this, right, let's figure out what dx d theta would be when theta is pi over 3. So let's see, that's 1 plus the sine of pi over 3 is going to be root 3 over 2. So that's going to be negative root 3 over 2. The cosine, plus, that should be a plus sign there. The cosine of pi over 3 is a half. So I get another half here. So let's see, what do I get there? I get 1 plus root 3 over 2, right, times negative root 3 over 2. So this times this is negative root 3 over 2. This times this is going to be 3/4, minus 3/4, right? Minus 3/4 plus a half times a half is a fourth. So this is negative root 3 over 2 minus a half, which is negative root 3 minus 1 over 2. So this is dx d theta. Okay, so we're going to hang on to that for a minute. Dx d theta is negative root 3 minus 1 over 2. So let's carry that over here. We have dx d theta being negative root 3 minus 1 over 2. Okay, so now let's play the same game with y. So y should be r, which was 1 plus sine theta, now times sine theta. All right, so it's r times sine theta. So dy d theta works out to be first times the derivative of the second plus the second times the derivative of the first. Okay, so dy d theta when theta is pi over 3, so let's see, that's 1 plus sine of pi over 3, which should be root 3 over 2, times cosine of pi over 3 is 1/2, plus root 3 over 2 times a half. Right, so let's simplify a bit here. That's a half plus root 3 over 4 plus root 3 over 4. Right, so that's going to give me a half plus root 3 over 2, which is 1 plus root 3 over 2. But dy dx should be dy d theta times d theta over dx, which should be 1 plus root 3 over 2 times 2 over radical negative root 3 minus 1. Those cancel. This is 1 plus root 3 over negative 1 times 1 plus root 3, which is just negative 1. So this means that as this curve is going around, when theta is pi over 3, the slope of the line that's tangent to this curve is negative 1. We actually got a dy dx out of an r of theta type function. So sometimes and oftentimes that's the goal when working with polars. So you have to be careful. Do you need dr d theta or do you need dy dx? Dr d theta, you just take the derivative, right? Dy dx, you have to break it into two parameters. X is r cosine theta, y is r sine theta. Find dx d theta, find dy d theta, use the chain rule, combine them, and get dy dx. Okay, so that's kind of cool. All right, so let's talk about parametrics. Okay, so remember parametric equations tend to be, so we're doing parametrics now. All right, parametrics. Tend to be written in the form of like x is some function of t and y is some other function of t. And there's like three possible derivatives that can come out of this. You can get dx dt, dy dt, and dy dx. Okay, dx dt is the shift right with respect to time, right? This is the shift up with respect to time. And this is the slope of tangent line. Okay, so that takes a little bit of thinking, but each of these derivatives indicates something different when you look at the picture. All right, so we need to be aware of these. Now, calculating these is not so challenging. Dx dt is just f prime of t, right? You just take the derivative of f with respect to t. Dy dt then is g prime of t. And to get dy dx, well, you got a formula for getting dx dt and a way to get dy dt. So dy dx should then be dy. Oop, that should be crazy. All right, so this should be dy dx, right? There we go, dy dx should be dy dt times dt dx. So it's this, right, times the reciprocal of that. Okay, so that's just chain rule. Those things fall out. Life is good. All right, so let's look at this in a practical example. All right, so let's let x be t squared, let y be t cubed minus 3t. So dx dt is 2t, dy dt is 3t squared minus 3, which means dy dx is going to be 3t squared minus 3 over 2t. See? Pretty painless, right? So let's say, what if we do, what happens if I'm at t equals 1? Then dx dt is 2, which means that I'm going up 2 units per second. Or sorry, right 2 units per second. Dy dt would be 0. So that means I'm not moving up or down at all over time. And dy dx means that my slope at that point, so that's 0 over 2, which is 0. My slope at that point is 0, which means that the tangent to the curve at that point is horizontal. All right, so that's pretty straightforward. The second derivative runs into a similar problem that we've seen earlier, like when you did implicit differentiation. So let's take a look at that. So let's look at an example for the second derivative. Let's let x equal cosine t. Let's let y equal sine t. Okay, so this is like the unit circle. All right, so dx dt is negative sine t, right? Dy dt is cosine t, which means that dy dx is the cosine t cosine t over negative sine t, which means it is the negative cotangent of t. Okay, so if I take the second derivative of that, let's see, the derivative of the cotangent is the negative cosecant squared of t, and then I take the derivative of the inside, because this is implicit, so this is going to be dt dx, but we know dx dt, so I just multiply by the reciprocal of that, so this is the cosecant squared of t times 1 over negative sine t, but the cosecant is already 1 over sine t, so this is going to be negative 1 over sine cubed t. We have 3 of those in the bottom. So there we go. We found the second derivative of dy dx at time t. So working these derivatives are largely a matter of just taking count of which variable you are taking the derivative with respect to. Usually in the polar case, you're taking the derivative with respect to theta. In the parametric case, you're usually taking it with respect to t, and then appropriately leveraging the chain rule when appropriate to get to other derivatives like dy dx or the second derivative of d2y dx squared. So this is kind of ground zero for polars and parametric equations and their derivatives.